Okay, so now we're in chapter 3.2 and it's on conditional probability and the multiplication rule. Our objectives, we're going to determine conditional probabilities, distinguish between independent and dependent events, use the multiplication rule to find the probability of two events occurring in sequence, and use the multiplication rule to find conditional probabilities. Alright, so the definition, conditional probability. It is the probability of an event occurring given that another event has already occurred. It is denoted as P, meaning the probability of B, given this line right here, this vertical line, reads as given A. So the probability of B given A. So example, the probability that I will carry an umbrella today, given it rained last night. So we're trying to determine the probability of me carrying an umbrella. Given that something happened last night, what was it? The rain. Independent and dependent events. So independent events are the occurrence of one of the events, the occurrence of one of the events does not affect the probability of the occurrence of another event. So for example, the probability I carry an umbrella with me today, given you ate pizza last night. They have absolutely nothing to do with each other. Therefore, the event of me carrying an umbrella and the event of you eating a pizza are independent. Another one, the probability of rolling a 6 on a fair die, given that I flip a fair coin and get heads. So let me read that again. The probability of rolling a 6, given that you flipped a coin and got heads. Well, these two events are independent because the occurrence of me, the actual chance of me getting a 6 is not affected by me flipping a coin and getting heads. If I have the probability of B given A equaling to the probability of B, or if the probability of A given B is equal to the probability of A, then my events are also independent. Let me erase this out of our way. Let me read that again. So if the probability of B given A is equal to the probability of B, then A and B are independent. Why is that? Because technically this probability has nothing to do with my probability of getting B, and they come out to be equal. And we can also see it this way. The probability of A given B, you see B has already occurred, but it's still equal to the probability of A, which means B had no effect in the probability of A. So these guys are also independent. The probability of the given doesn't change anything, basically. The probability of A over here as a given did not change the probability of getting B, and the probability of my given B did not affect my probability of A. Events that are not independent are dependent. Okay, so the multiplication rule. The probability that two events A and B will occur in sequence is the probability of A and B is equal to the probability of A times the conditional probability, which is the probability of B given A. So it's the probability of A times the probability of B given A. For independent events, the rule can be simplified to the following. The probability of A and B is equal to the probability of A times the probability of B. Why, for independent events, can we replace the conditional probability with the probability of just B? Well, remember, when events are independent, the outcome of the given does not affect the actual probability of B. Therefore, I'm kind of ignoring this, right? And the probability of B just falls down. And of course, this can be extended for any number of independent events. The probability of A and B and C is equal to the probability of A times the probability of B times the probability of C. Alright, so let's go in our books to page 152, and we're going to look at some practice problems. We're going to start by looking at number 7, and it says, the table shows the number of male and female students enrolled in nursing at the University of Oakland Health Sciences Center for a recent semester. So hopefully we're all looking in our books and we see the table. And part A says, find the probability that a randomly selected student is male, given that the student is a nursing major. So, how do we deal with conditional probabilities when given a table? So this is what we're going to do. The first thing you want to do is isolate the table to only consider the given. So isolate the given. So that's step 1. Isolate the given. So it says, given that the student is a nursing major. So the given is that the student is a nursing major. So go ahead and find the nursing majors in your table, and all I'm going to do is just write that part. 94, 725, and 819. This is the total. These were females, and these were males. And these are my nursing majors. Okay, so isolate the given, and then step 2 would be to find the actual probability that you're looking for. So what I'm going to do is change my color of my pen, and it wants the probability of male given a nursing major. So I isolate the nursing majors. Those are the only ones I'm considering. Remember, the given means it's already occurred. I know the student's a nursing major. Well, how many total nursing majors are there? 819. So remember, the whole goes on the bottom, and the part goes up top. So 819, that's from the total. And then you got to figure out how many of them are males. 94. So you get 94 up here. Now let's get our calculators out, and we'll calculate what that is. And it comes to be 0.115. So this is approximately 0.115. Alright, part B. It says, find the probability that a randomly selected student is a nursing major given the student is a male. So this time they flipped it on us. So this time we have still a conditional probability. We're still working with the table. So the first thing we want to do is isolate the given. This is where you always start with your conditional probabilities. Let's isolate the given. This time the given was that the student is male. So I know for a fact that the student's male, so I'm going to isolate the males. We have 94, 1104, and then 1198. This is the total. These are the non-nursing majors, and these are the nursing majors. Okay, so we isolate the given, and then we come back and we're going to look for the probability that we're actually interested in. And it says the probability a selected student is a nursing major given the student's male. So I know the student's a male. That's already happened. How many males were there? 1198. And of those, how many were nursing majors? 94. So now we have 94 divided by 1198, which is approximately 0.078. Notice the difference in the two answers when you change the given. So before our given was nursing majors. Now our given are males. And we see the change in the answers. So flipping these or switching these will not always result in the answers being equal. All right, number 9. So number 9 says, determine whether the events are independent or dependent. Explain your reasoning. And it says, selecting a king from a standard deck of 52 playing cards, replacing it, and then selecting a queen from the deck. Are these events independent or are they dependent? Well, because we are replacing the king, the probability of selecting a queen is not affected. Therefore, the events are independent. And let me go a little bit further to explain that some more. What is the probability of selecting a king out of the standard deck of 52 cards? Well, there's 4 kings in there. So that probability is 4 out of 52. Now, you replace the king. Therefore, how many cards are still in your deck? 52 of them. So the probability of getting a queen is 4 out of 52. Was the probability of getting a queen affected because I selected a king? No, that's only because you replace. Now let's take the instance where we actually do not replace the king. Let's see what happens if there's no replacement. Well, this time, the probability of getting a king, that's still 4 out of 52. I select the king first. Now, I did not replace the king. So how many cards are now available to us? 51. So the probability of getting a queen is 4 out of 51. It's affected by taking a king first and not replacing. Therefore, this would have actually been dependent. So the key word that made this independent was, or the key words, was that you were replacing the king. You're putting the king back into the deck. If you do not put the king back, then they are actually dependent. All right, number 13. It says rolling a 6-sided die and then rolling the die a second time so that the sum of the two rows is 5. Well, are these events independent or dependent? Well, I'm going to roll a die and then I'm going to roll the same die a second time, but I want the sum to equal 5, which means whatever I get on my first die or my first row affects the probability of the second, right? So let's say I roll a 4 on the first row, which means what would I need on the second row in order so that the sum would be 5? I would need to roll a 1. Well, shoot, let's say I roll a 2 on the first row. Then I would need to do what? Roll a 3 on the second. You see these events? They rely on each other, or the second event relies on the first. Therefore, these are dependent. All right, let's look at number 16. It says, identify the 2 events described in the study. Do the results indicate that the events are independent or dependent? And it says, stress causes the body to produce higher amounts of acid, which can irritate already existing ulcers. But stress does not cause stomach ulcers. So what are our 2 events? They're talking about stress, and they're also talking about stomach ulcers. So we have our 2 events. I'm going to call it event A, stress, and event B, ulcers, stomach ulcers. Now, are they independent or are they dependent? Well, what did they say? They say stress does not cause stomach ulcers. It can irritate already existing ulcers, but they're not going to create new ulcers. Therefore, these are independent. Okay, number 19. And it says 2 cards are selected from a standard deck of 52 playing cards. The first card is replaced before the second card is selected. Find the probability of selecting a heart and then selecting an ace. So in this problem, they actually want us to find some probabilities. Okay, so let's see here. Our 2 events, well, the first event is selecting a heart, and then the second event is selecting an ace. So I have event A is selecting a heart, and event B is selecting an ace. And they want the probability of selecting a heart and then selecting an ace. So the probability of selecting a heart and an ace. So let's start the probability of a heart. Remember, because we're replacing the heart, these 2 events are independent. Because we're replacing the heart in the deck, these events are independent. Which means we can use the multiplication property to find the probability. We start by finding the probability of selecting a heart. Well, there's 52 cards in the deck. How many total hearts? There are 13. And then times, because remember that's what the principal told us to do was multiply. You can think of the word and like multiply. The probability of selecting an ace, well, we're replacing the heart back in the deck, so we still have 52 cards, and there are 4 aces there. So this comes out to be 1 out of 52, which is approximately 0.019. Let's keep going. Let's look at number 23. So number 23 says, in a sample of 1,000 U.S. adults, 180 dine out at a restaurant more than once per week. 2 U.S. adults are selected at random without replacement. So I'm just going to write down that my whole, or my total, is 1,000. And it also told me 180 dined out at restaurants more than once a week. Okay, so of 180 dined at restaurants, how many didn't dine at restaurants more than once a week? Well, it's going to be 1,000 minus 180, which is 820. All right, now let's go to part A. Part A says, find the probability that both adults dined out more than once per week. So the probability that both adults dined out more than once. Well, probability of both adults dining, so I'm going to call it probability of event A times B. This is adult A dining out, and this is adult B dining out. First, we have to find the probability that the first adult dines out. Well, how many total people were surveyed? 1,000. That's the whole. How many of them dined out? 180. Times, because remember the word and multiply. This time, how many adults are actually left? 999. Of the 180 that dined out, how many are now available that dined out? 179. You see how we count down 1? is like saying this adult, adult A, dined out, therefore I take him out of my group. I've already looked at him. I have 179 left, and I have 999. You multiply these together, and we get approximately 0.032. Part B. It says find the probability that neither adult dines out more than once per week. So this probability, again, I'm going to use C and D this time. This is just notation. Well, the probability that neither adult dined out. Okay, so the probability that the first adult didn't dine out. Well, how many adults were there? 1,000. And how many of them didn't dine out? 820. Times the probability that the second adult didn't dine out. Well, this time there's 999. And since we started with 820, we got to subtract 1 because we already looked at the case of the first adult. And now we have 819. Multiply these together and we get approximately 0.672. Alright, part C. It says find the probability that at least one of the two adults dined out more than once per week. So at least one. Well, what does at least one means? It means one or two. It's one or more, but how many adults are we surveying? Only two. So it's one or two. Now this seems like a lot of work to do, so consider the complement. Remember, the complement is 1 minus the probability of the event. Well, what's the opposite of at least one? You say at least one considers 1 as well as 2. Who do you not see here? 0. So this will be the probability that none of the adults dined out. That was what we got in part B. So the probability of at least 1 will be equal to 1 minus the probability that none actually dined out. So that was 1 minus 0.672 and approximately 0.328. And then part D says, which of the events can be considered unusual? Well, remember, unusual means the probability of the event happening is less than 0.05. Less than or equal to 0.05. Any of these less than 0.05? Part A, therefore part A will be considered unusual. Alright, let's go down to number 26. And it says, in a sample of 2016 U.S. adults, 242 said Richard Nixon was the worst president since World War II. 3 U.S. adults are selected at random without replacement. So it says, part A, find the probability that all 3 adults say Richard Nixon was the worst president since World War II. Well, let's do the same thing. Let's write down the information they gave us. The total was 2016. A total of 242 said he was the worst, which means how many are saying he is not the worst? So we're going to do 2016 minus 242. And we get 1,774. All right, part A. And it says, find the probability that all 3 adults say Richard Nixon was the worst president since World War II. So we need the probability of A times the probability of B times the probability of C, because we have 3 different probabilities, or 3 different events, and they're all independent because we are replacing. We're not replacing, therefore they're actually dependent. So I take that back. So the probability that the first adult says Richard Nixon was the worst, well, there's a total of 2,016 adults. 242 said he was the worst. So then the probability of the second, well, now we got to subtract one off because we didn't replace that adult. He's already been taken off, which means we got to do the same here. And then for the third, we still have 240 times 2014. We multiply this out and we get approximately 0.002. And then part B. It says find the probability that none of the three adults say Richard Nixon was the worst president since World War II. So none, we're going to do the same thing as we did in part A, but this time our part has changed. We still have 2016 adults. For the second, we'll have 2015. And for the third, we'll have 2014 still. But the numerators changed. Therefore, let's see. How many adults said he was not the worst? Or none of the adults said that he was worse. That's 1,774. So then the second will be 1,773. And then 1,772. If we multiply this out, we'll end up with 0.681. And then part C says, find the probability at most two of the three adults said Richard Nixon was the worst president since World War II. Well, what does it mean to be at most two? My pen's messing up, I apologize. So at most two means 0, 1, 2. Again, it seems like a lot to do, so we're going to consider the complement. So the complement would be 1 minus, or the probability of at most two would be 1 minus the complement, which is, well, what number do you not see here? We're missing a 3, which means all 3 said that he was the worst. So that's what we did in part A. So that's 1 minus 0.002, and we get 0.998. And of course, part D says which of these events can be considered unusual. Well, any probability that's less than or equal to 0.05 is considered unusual. So it'll be part A is unusual. The probability that all three adults said that Richard Nixon was the worst since World War II. Okay, so here's a summary of what we did in 3.2. Please email me if you have any questions.